So we're back to talking about waves in a magnetized fluid. We've already looked at sound waves, which are waves in an unmagnetized fluid, and now we looked at this slide yesterday, the last time we met, and as we remarked, the continuity equation is exactly the same, no difference at all. This is the continuity equation, and this in particular is a linearized continuity equation. It's no different from how it was earlier. The linearized equation of motion, which is the momentum equation, that contains this extra part. This is the extra term. Extra with respect to an unmagnetized situation, that's all, right? It arises from the Lorentz force term, which is J cross B, right? But this is not J cross B itself. This is something that needs to be kept in mind. This is the linearized version of J cross B, and J is simply curl of B, right? So, so that's the extra term, and so the linearized equation of motion, neglecting viscosity of course is that, and the linearized induction equation is this. Okay, so now before going on, what we did was we said it's simple to split up these vector equations in components x, y, and z, right? Recognizing that the magnetic field is only in the z direction. Okay, so the magnetic field is just in the z direction, and all we're doing now is writing down the equations in blue, this, and this, in components. That is all. So it's somewhat lengthy but straightforward really, and the first thing to realize now is that, you know, these two equations in red, right? So that was the comment that I made last time. It's somewhat lengthy but straightforward. It is really no big issue to write down these three equations in component form. The remarkable fact right now is we will consider magnetosonic waves in due course, but at the moment the remarkable thing to recognize is that the y components, you know, of these two equations, this arises from the induction equation, and that arises from the continuity equation. The y components of the velocity and magnetic field are not coupled to any of the other components. You see, you have Vy here and you have delta By here. You have delta By here and Vy here. They don't talk to, there is no appearance of delta Bz or anything, or for that matter Vz in these two equations. So that's what one means by saying that the y components of the velocity and magnetic fields are not coupled to the other components. Another way of thinking about this is to say that you can simply set the x and z components of the velocity as well as the magnetic field, perturbations, and for that matter even the pressure perturbation and the density perturbation equal to 0. And still you can expect a non-trivial solution for Vy and By. Okay, so this is also pointing to the fact that here we are concerned only with delta Vy and delta By. That is it. In other words, you have a magnetic field pointing in the z direction, right? Z hat, and so this would be the right. And suppose this was the y direction. Okay, so we are considering a perturbation of the magnetic field that looks like this, right? So in other words, you only have, so this is the y direction, right? So the magnetic field is perturbed in the y direction, you see, and the velocity also. The velocity is also perturbed in the y direction. So, this is the situation that we are considering. Okay. In other words, transverse perturbations. We are talking about perturbations of V and B. That's what one means by this, right? Transverse to what? Well, transverse to the uniform magnetic field direction. Okay, so that is the main thing I want to emphasize here, right? And so we are considering a mode that arises only from transverse perturbations of V and B. This gives rise to the Alfvene mode. This is a very important mode of wave propagation, and let us now go ahead and see what the properties of this Alfvene mode are. Right. Alternatively, I would say never mind this slide. This is an exact thing as this. Okay, written in a slightly different form, written in terms of theta, which is the angle with respect to the z-axis, and we have already introduced the Alfvene velocity and the sound speed is exactly the same. Okay, so you have this matrix multiplying the velocity vector, and that's equal to 0. And so, in order for a non-trivial solution to exist, the determinant of this matrix needs to be 0. So, it's an equivalent way of representing it. We will not, I just wanted to show it to you, but we will not concern ourselves with this way of representing it anymore. Okay. So, the thing is, when you look at these two equations, right, these are two coupled first order equations, and you can you can parlay them into one coupled second order equation, exclusively in delta Vy or exclusively in delta By, and that's what this is. So, you have an equation which looks like d squared dt square of delta By minus this quantity Va squared times d squared dz square of delta By equals 0, or the very same equation with delta By replaced by Vy. That is it. Okay. Where this all important thing Va squared, this is the Alfvene speed. Okay. It looks like the sound speed but there are important differences. And let us see what those differences are. Right. So, you see the sound speed, if you remember, was written as Cs squared was dP d rho, which we sort of carelessly can write it as P over rho. Okay, where this was the gas pressure, and this is the density, gas density. Whereas the Alfvene speed, which we just defined, is given by b squared over 8 pi. I beg your pardon, I wonder if it's b squared over 8 pi, b squared, yeah, 4 pi, sorry. So, it's b squared over 4 pi divided by rho. So, you see this and that look very similar. So, the rho appearing in the denominator is the same, and this is the magnetic pressure In what sense this is the magnetic pressure? If you remember, we wrote down the magnetic stress tensor, right? And this would be the diagonal term in the magnetic stress tensor. Okay, and you know that in any kind of pressure, the diagonal term is interpreted as the scalar pressure. Okay, so in that sense, this can be interpreted as the magnetic pressure. So this and that, the expressions for the Alfvén speed and the sound speed look quite identical, except there are differences. There are important differences. Important differences. The sound wave is longitudinal, right? In other words, the k, the propagation vector of the wave is along pressure and the sound wave essentially, let me finish this. In other words, the density and pressure perturbations are along the direction of propagation. Okay, whereas here you see an Alfvén wave, by definition, that is the direction of propagation along. So this wave, it travels along the z direction, along the direction of the unperturbed magnetic field. But the perturbations are transverse. You see, the perturbations are in the y direction. So the Alfvén wave is transverse. So this is one very important difference between the sound wave and the Alfvén wave, although the expressions for the sound speed and the Alfvén speed look quite similar, simply with the magnetic pressure replacing the gas pressure. Okay, but the nature of the waves are quite different. So this is something that I wanted to sort of emphasize. And it's the Alfvén wave is much like a wave on a string, right? That's exactly what say you have a string like this, and fastened at both ends, and so it has a certain tension on it, and you twang it, right? You give that kind of a perturbation to it, and you have as a result you have waves propagating like this. Those would be waves on a string, and that looks exactly like the Alfvén wave. You see, the magnetic field is like a string in the z direction, and it's as if the magnetic field, which is an elastic kind of a thing, the magnetic field line, which is like a rubber band, it's being twanged, and transverse perturbations on this rubber band are propagating along the magnetic field direction, right? So so in that sense, the Alfvén wave is much like a transverse wave, I should say, transverse wave on a string. Okay, so this is something important to keep in mind as we go ahead. The other things, some other salient properties of the Alfvén waves are that the fractional amplitudes are similar. In other words, delta By over B is the same as Vy. I simply write Vy because there's really no need to write delta Vy. There was no average V to start with, so the small Vy is indeed a delta quantity. Okay, and an immediate consequence of this is that there's equipartition between the kinetic and magnetic energies. In other words, the energy in the magnetic field perturbations is delta B squared over 8 pi, right? And the energy density, actually, I should say energy density, energy densities to be precise. I've been a little, it's not so much energies, but it's really should be energy densities. There's a bit of a loose way of saying it. So the delta B squared over 8 pi is the energy density in the magnetic field perturbations, and half V squared energy densities again per unit gram, per unit mass. So this, as you can recognize, is the kinetic energy per unit mass, right? So this would be energy density, specific energy densities, and there's equipartition. Okay, the magnetic energy density and the kinetic energy density are the same, and this is a simple consequence of this fact. Okay, Alfvén waves are also dispersionless. If you assume e raised to I k x minus I omega t, this kind of dependence for the delta by as well as the vy, what happens is this d square over dt square becomes minus omega square, right? And sorry, omega square just becomes omega square, and the d square over dz square becomes minus k square, and so just from this you can figure this out. Okay, this is the dispersion relation, and as with, again, this is similar to the sound mode. As with the sound wave, rather, the sound waves are also dispersionless, and so are the Alfvén waves. The omega over kz or the d omega over dkz are both not functions of omega itself. They simply involve the Alfvén velocity. However, please remember this is kz, not k. Not k itself. This is k only along the z direction, only along the magnetic field direction. So please, this is one important difference between the sound wave and the Alfvén wave. Okay, so the dispersion relation for a sound wave is omega squared equals c sub s squared k squared, like that. Alfvén wave is omega squared equals va squared k z squared. Very important. Okay, first of all, the whole point is that the Alfvén wave is like a transverse wave on a string, and the string is the magnetic field. So the appearance of a magnetic field breaks the symmetry. Here the k is the same in all directions, you see. There is nothing to distinguish one direction from the other. Here the presence of a magnetic field immediately sets a preferred direction. Okay, so it breaks the symmetry, and so the k in one direction is not the same as the k in other directions. Okay, specifically the k along the magnetic field is different from the k perpendicular to the magnetic field, and here we are referring to kz, in other words, the k along the magnetic field. Okay, so this is very important to keep in mind. So kz, not k, right? It involves only k sub z, yeah. So that's clearly the case. In other words, the waves propagate along the magnetic field, like we have said, and its transverse, the delta b and v, are perpendicular to k as well as to b, as we have already remarked. They are much like waves on a string. Okay. The other thing is that the other important difference is that there is no appearance of delta rho. There are, if you remember, we could here, you see, we had set, we could get non-trivial solutions to these two equations with delta rho actually being equal to 0. No density perturbations. That's one way of looking at it. The other way of looking at it is that nowhere in this equation does delta rho make an appearance, right? So therefore, Alfvén waves do not involve density perturbations at all. Therefore, Alfvén waves are incompressible. Very, very important point. And this is an important point of distinction with the sound waves. Sound waves are compressible. That's the whole point of sound waves. Okay, sound waves involve compressions in density as well as delta rho and delta p. Here, neither delta rho nor delta p makes an appearance. So Alfvén waves are incompressible. Okay, so although the expressions for the Alfvén speed and the sound speed look similar, there are several points of difference between the sound speed and the Alfvén speed, and these are important to note. Right, so let's go ahead. This is a picture of Hans Alfvén. He won the Nobel Prize in Physics in 1970 for many things. But I urge you to look up this website, very interesting website which contains his Nobel Prize lectures, with the lecture he delivered while accepting the Nobel Prize, and it's called Cosmical Electrodynamics. It's very instructive. I would strongly urge you to go through it, at least glance through it once. Right, okay. So now let us now move to the non-Alfvén wave solutions. Remember, we split up the three equations in components, and we marked only the ones which involve only the y components. We marked them in red. Now how about the other solutions, right? So we marked the ones which involve only the y components, and we marked them in red, and we found that they represent Alfvén waves. They represent a particular kind of wave which is transverse, which, in other words, the perturbations are transverse, the velocity and the magnetic field perturbations are transverse, like this, right? And involves that they are transverse and involve no delta p and delta rho, so they are incompressible. Right, and so these are this is just to these are Alfvén Alfvenic perturbations. Okay, now it turns out that the other solutions are consequences of compressibility. In other words, unlike the Alfvén solution, the appearance of delta p is very important. Unlike the Alfvén wave. The Alfvén wave was incompressible. There was no need to invoke a delta rho and a delta p. Here, the delta rho is central, as we will for these particular kinds of waves. It's easier to proceed using Fourier components. In other words, wherever you see d over dt, you write it as I omega. Wherever you see a d over dx, you write it as an ik. Okay, and there can be a minus I omega or there can be a minus ik, depending upon exactly how whether you're writing e raised to I omega t minus kx or e raised to I omega t plus kx, but it doesn't matter. So this is essentially what I mean by this. Okay, so instead of the differential equations, you'll get algebraic equations, and the only slight disadvantage there is that you will be dealing only with one temporal frequency and one spatial frequency, or spatial wave number. Okay, only with one value of omega and one value of k at a time when you're doing Fourier components. But that's okay, the equation is linear, so the behavior for other frequencies, spatial and temporal, can be then superposed, linearly superposed. So you have the solution for one, the solution for the others look exactly the same. The functional dependencies are exactly the same. That's the whole advantage of doing Fourier language, right? So I assume that it's an exponential I omega t minus k dot x, right? So therefore, all time derivatives of I omega and all space derivatives are minus I k, right? So in this language, the linearized mass continuity equation, which is this, becomes that, right? So it's quite simple. The d over dt became an I omega, and the divergence of v became a ik times v. That is it. So that's how you get this. This is the same thing as the mass continuity equation. So this is really the mass continuity linearized continuity equation in Fourier language. That's what this is. Instead of rho, we can rather instead of delta rho, if we prefer to write things in terms of delta p, then you have to invoke the sound speed. So, so this is the same as this, except you have now invoked the sound speed to eliminate the delta rho in favor of delta p. So, this again is the same equation, linearized continuity equation in Fourier language. Okay. So, just to recap, we are looking at the same system of equations. Except we had originally looked at this and this. These gave the Alfvén wave solution. Right? This equation and this equation, they together they gave the Alfvén wave solution. Now what we are going to do is we are going to look at the remaining equations, which is this, 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 and this. Okay. And what's more, we are not going to bother about, just for convenience rather, we will not look at the differential equations themselves. We will look at the Fourier analyzed versions of the differential equations, where the d over dt becomes an I omega t and the d over dx becomes an ik. Okay. So, and the other important thing to remember is that you have the appearance of delta p's here. You see delta p's or delta rho's for that matter. You have a delta p here, you have a delta p here. So, therefore, clearly these modes do involve pressure and density perturbations, and these are central to the understanding of these modes, and therefore, these kinds of modes are necessarily compressible. Okay. And these modes are called magnetosonic modes. Sonic because they are like sound waves in that they involve compressibility, and magnetosonic in that they are sound waves modified by the presence of a magnetic field. And so these magnetosonic waves are split into two varieties. One is a fast magnetosonic wave and one is a slow magnetosonic wave, and we will discover soon enough that they have very interesting properties in some particular situations, depending upon the angle of propagation of the wave with respect to the large scale magnetic field. The magnetic field again is always along the z direction. Okay, that can always be assumed without loss of generality, depending upon the direction of propagation of these magnetosonic waves with respect to the magnetic field, of course. Sometimes they start looking like the sound waves, sometimes they don't. Sometimes they look very much like the Alfvén waves. So, we will analyze these solutions when we meet next. So, for the time being, that is it. Thank you.